All right, so we're going to discuss the transient response characteristics of second order systems today. So with that, I would hope that you remember what we studied in the last one. So we shall actually proceed from what we discussed in the last one. All right. All right. So with that said, today we are going to figure out how to do an inverse Laplace transform to find out the step impulse response and the step response of a second order system without any zeros, right? So we defined the second order transfer function this way. If you recall that this is the form we chose for our second order transfer function. We had a gain factor, so we wrote this as p, okay, and with that we had omega n square, and I said we are going to discuss all these terms and what the significances are. We shall discuss all this in today's class. All right, so that was the standard form of a second order transfer function where there is no zero, okay, there is no finite zero here. Okay, so again the terms we have, or rather the parameters we have apart from this p are this zeta and this omega n. These are arbitrary parametric constants essentially, right? Again, you know that for transfer functions s is the transfer function variable, so essentially that is what we get after applying Laplace transform on the differential equation that defines the mathematical model of the system. But here we have two parameters, namely the zeta and the omega n, right? And for the moment we are going to skip this p here, because understandably this p, that multiplication factor here, that gain factor, essentially multiplies the output by that value p. So whatever output I get out of this, okay, right, if I keep that and if I want to figure out what will be the output of the system when there is a multiplying factor here, whatever, like that, something like that, then all we need to do is to magnify the amplitude of the response. So you already know that how to actually multiply signals with certain amplitude correcting factors, right? Amplitude modification factor. So that is what it is, right? So essentially we're going to get rid of that quantity here, okay, for our analysis here for the most part, and then we are going to bring that part back in once we actually develop our tool for the entire analysis here, right? But if you in case you don't recall, these two factors, or rather these two parameters, are called, so this zeta, okay, again this is a Greek letter zeta, this is known as the damping ratio, and this omega n is known as the undamped natural frequency. All right, and I'm going to explain all these terms properly. All right, and we are going to look through this with the examples we derived for electrical systems and mechanical systems. All right, again during the class, whenever you think something is missing or you don't understand something, feel free to ask. I shall definitely clear up your queries here. All right, so you have this. Now of course for this course I should have done the impulse response and the step response, but I shall keep the impulse response, I shall keep it for you to figure out what the impulse response would be, okay, because once we figure out the step response, impulse response is just a derivative of that, or you can just invert this transfer function, you will get the impulse response. That is something. So we are going to only look at the step response of the systems, but again you have to remember that it will be your homework to figure out the impulse response of this system, right? Now of course we have two parameters here, and depending on what values for those parameters are chosen, the response will look very different, okay, the response of the system will look very different. Now we are going to figure out the step response of the system, so essentially we are looking for the step response. So essentially we are talking about the response of the system when the input is a unit step signal. So basically you have xt to be equal to ut, right? And someone is asking why omega n square, why not omega? I am going to explain that term, right? So again, just in case you, oh, okay, just a moment. So here it will be omega n square. Very sorry, really sorry. Yeah. And here, of course, if I have omega n, in that case, I would have to write something like root over omega n. Okay. Again, this has certain significance, and that is why we have omega n square instead of omega n. We are going to discuss those terms properly, so don't worry. So for you, again, so we are starting our discussion today with a homework. So essentially, your homework would be to figure out the impulse response. So that will be your homework, first of all. Okay. Of course, once you understand how to figure out the step response, figuring out the impulse response won't be very difficult. All right. So we know that the Laplace transform of the input signal would be 1 by s, because that's a unit step. And again, for impulse response, the Laplace transform of the input would be just 1, right? So all you would need to do is to invert this transfer function itself, because if you do a Laplace inverse on a transfer function, you essentially get the impulse response of the system. All right. So I think that's easy to understand, right? Not very difficult at all. All right. So what we are looking for essentially is the output of the system, and the output of the system is nothing but the in Laplace transform domain, in the frequency domain, is nothing but the product of the transfer function and the Laplace transform of the input. Now, of course, the Laplace transform of the input is 1 by s, and the transfer function rather looks like this. Yeah, it's a product, right? So I can interchange the order here. So this is going to be s square plus 2 zeta omega n s plus omega n square, and we have omega n squared. Once again, you have to understand that I am just removing the scaling factor here. That can be brought in anytime I want, just by scaling the output, right? Because Laplace transform is a linear operation, right? So if you scale the input by a certain value, the output is also going to scale by a certain value, right? All right. So that is what it is, right? Now we have to figure out the inverse Laplace transform of this complicated thing. All right. But you have to understand that the inverse Laplace transform, I mean, figuring out the inverse Laplace transform won't be easy if we don't impose certain conditions on zeta, right? Now, for our purpose, zeta is going to be only positive, because if you recall in our earlier discussion, this term came from something like this zeta omega n. This term for electrical systems, we had something like if you recall, for that Rlc series circuit, this term was essentially 1 by L. Hold on, that was s square plus rc by lcs plus 1 by lc. So I can conclude C. So this zeta omega n, 2 zeta omega n was essentially r by l. So again, resistance cannot be negative, and inductance cannot be negative. So essentially all these terms we are dealing with are positive. Okay, could be 0 at most, but they're positive. Okay, rather greater than equal to 0 for our purpose. Okay, so now we are going to invert this in order to figure out what the response of the system is under certain conditions imposed on zeta. And why not on omega? You will see what I mean. Okay, so the first condition let's impose on this is when, just one thing. My laptop was showing a certain weird issue at this moment. Okay, all right. So condition one is when zeta is equal to 0, right? When zeta is equal to 0. If I have this condition, of course, the minimum value it can have is 0, right? If I have this condition, and you will see why these conditions are chosen this way, that will be evident while we actually figure out the inverse Laplace transforms. Okay, all right. So here under this condition, we have ys. When zeta is equal to 0, I have ys is equal to 1 by s into omega n square plus s square plus omega n square. So essentially this entire term actually vanishes. All right, this entire term actually vanishes, right? Very easy to understand. Now, of course, in order to figure out the Laplace transform of this thing, we have to invert this. I mean, do a partial fraction on this, right? We have to do a partial fraction on this. I think you understand what I mean. Okay, let's do a partial fraction. Let's assume that this is like a by s plus bs plus c by ss square plus omega n square. And of course, the denominator on the next part here is a non-factorizable second order polynomial, right? So this does not have any rational factors other than this one and one. So essentially this is the partial fraction expansion, right? So again, with that said, let's do the arithmetic on the the algebra on the partial fraction expansion. And of course, if I just simplify this, we are looking for omega n square such that this can be derived from a into ss square plus omega n square plus s into bs plus c. So that would be the numerator if I consider this type of partial fraction here, and that numerator is essentially omega n square. So this is essentially omega n square. Again, this is an identity, this is not an equation. So this is supposed to be true for every possible value of s, and for that, with that in mind, we are going to figure out the values for a, b and c. Got it? All right, so let's choose a certain suitable value for s. Since it's true for every possible value of s, let's choose, so for example, s equal to 0. If I choose s equal to 0, then this term vanishes. I have a multiplied with omega n square, and that gives me omega n square, which tells me that a will have to be 1. So right off the bat, we have figured out one of the factors, right? All right. Now figuring out the rest of the factors is slightly difficult, okay? But we are going to employ another technique here to figure out the rest of the terms here, okay? So look at the left hand polynomial on the left hand side of this identity, okay? This is again identical, keep in mind, okay? Look at the polynomial on the left hand side of the identity. So we have figured out a. Now let's figure out what is the, let's ask this question, what is the coefficient of s square on both sides? The idea being, whatever happens on the left hand side will be identical to whatever happens in the right hand side, because this is not an equation. Again, once again, this is an identity, right? So whatever is the coefficient of s square on the left hand side will be the same thing. That would be the coefficient of the term with s square on the right hand side, essentially because this is an identity, right? So now look at this term. What is the coefficient of s square? That would be a. What is the coefficient of s square? That would be b. So the total coefficient of s square would be a plus b. But on the right hand side, this is identical to whatever is the coefficient of s square here. But what is the coefficient of s square on the right hand side? That's 0, right? The coefficient of s square is 0 on the right hand side, so that's a 0. So with that, I see that b is equal to minus a, which tells me b is equal to minus 1, right? Right. So with this we figured out this, with this we figured out this. Now we are still left to figure out the coefficient of, and we are still left to figure out the coefficient of the value of c, right? All right. So how do I figure out the value of c? Okay. Let's look at the coefficient of s on both sides. Coefficient of s on both sides. Okay. So what is the coefficient of s here? Of course, this polynomial does not contribute to the coefficient of s. What about this one? Of course, the coefficient of s here, because of this part, would be s into c. So of course, the coefficient would be c essentially. So on the left hand side, we have the coefficient of s to be c, and on the right hand side, what is the coefficient of s? That's a 0, right? So that's going to be 0. So these are the three values we essentially have. So this is basically 1 by s plus, so that's going to be minus s, because b is minus 1 and c is 0, divided by s square plus omega n square. Got it? Again, if you have any query, feel free to ask. Okay, we are keeping this calculation as a rough work. All right, hold on for a second once again. All right, so that is essentially our ys. So we are looking for yt, which is the inverse Laplace transform of ys. So we are trying to figure out the output of the system, and that would be the inverse Laplace transform of ys. So essentially we are looking for the inverse Laplace transform of this quantity. All right, this quantity, let's bring it here. We are looking for the inverse Laplace transform of this quantity, right? All right, so of course this minus sign can be brought here, so that becomes a plus. And of course so of course you know what the inverse Laplace transform of these quantities are, right? So this is of course 1 by ut, so this is 1 by s, so that's the inverse Laplace transform of it. This is ut, and this is s by s square plus omega n square, so that is going to be cosine of omega n t ut. So the output of the system is essentially 1 minus cos omega n t ut. Of course, what is the purpose of ut here? Just to denote that the output of the system is 0 when time is less than 0, right? When t is equal to 0, then the output of the system is non-zero, right? When t is greater than 0, then only the output of the system is non-zero. That's the output of the system when zeta has a value of omega n, right? So let's plot this. Let's try to figure out what the plot of this one would look like. Okay, what the plot of this one would look like. Now look at this one. So this is a pure sinusoid, right? Rather cosinusoid. Okay, and when t has a value of 0, what is the value of this cosinusoid? That's 1, right? And at certain intervals the value will become 0, and then again 1, 0, so and it will vary between -1 and +1. All right, so that's the cosinusoid, and we have 1 subtracted from that. All right, so let's try to figure out the response of the system properly. Okay, so let's try to figure out the response of the system. So let me draw the output here. So hold on for a second. I'm going to, okay. So all right, so again there is no point considering the output before t equal to 0 because that's 0. Okay, okay, now what is the maximum value of this output? Of course the maximum value of this output, hold on for a second, the maximum value of this output is essentially when this cosine omega nt is -1, then the maximum value of the output is equal to 2. And what is the minimum value of this entire output? When this cosine omega nt is equal to 1, in that case the output would be 0. So this output actually varies between 0 and 1, 0 and 2. Okay, so this output would actually vary between 0 and 2. All right, so let's say this is 0, this has the value, hold on. Okay, okay, this has a value, maybe not. And drawing is the most difficult thing on a tablet, at least for me. Okay, right, so we have t here, we have t here, and we have the output here. Okay, and of course let's consider the points at which this is going to become 0. Okay, and so again let's start with the discussion properly. Okay, fine, let's take these. Okay, right, now see, when t is equal to 0, the output has a value of 0, right? So this is the point we are looking for. At t equal to 0, the output is also 0. So this is the point we are looking for. Okay, now at t is equal to when t is equal to, for example, pi by 2 omega n, when t is pi by 2 omega n, look very carefully, when t is pi by 2 omega n, what is the value of the cosine omega n t? That becomes cosine pi by 2, but cosine pi by 2 is 0, right? So that's going to be 1. The output, the entire thing is going to be 1, right? So same, this is going to be 1. So this is at pi by 2 omega n. Now what about the value of, what about the value of the output when t is pi by omega n? So when t is pi by omega n, we have cosine pi, but cosine pi is -1, so the output is going to be 2. Output is going to be 2. So that's the point we are looking for. Okay. And similarly, when this is 3 pi by, time is 3 pi by 2, so this is going to be cosine 3 pi by 2. Okay, got it? So that's once again going to be 0. So the output at that point is going to be 1. Okay, and similarly again, when t is 2 pi by omega n, that's going to be 0. Output is going to be 0 because this is going to be 1 at that point. Okay, so essentially what we are doing, we are using a school level geometry, trigonometry here. Very simple school level trigonometry, right? All right, so these are the points we have. Now, of course, drawing this is slightly difficult for me. Let me try my best. This kind of requires very high concentration. Nice. All right, so now with that said, let's put the values of the time here. So time is pi by 2 omega n here. At this point, time is pi by 2 omega n. So at this point, time is pi by omega n. At this point, time is 2 pi by omega n. At this point, sorry, hold on. Do I need to zoom this? At this point, the time is 3 pi by 2 omega n. At this point, time is 2 pi, or rather pi by omega n, pi by omega n, and so on, right? So on, right? Fantastic. So one complete period of the signal would happen here. So this is 1 half cycle and this is 1 half cycle. So one complete period of the signal would happen here. So that's going to be 2 pi by omega n, right? That's 2 pi by omega n. All right. So that is what the output signal looks like. Let me take this, remove that place. Okay, and here the value of the output is 2, here the value of the output is 1, and here the value of the output is 0, right? So that's the output of the system when there is when the value of zeta is equal to 0, right? When the value of zeta is equal to 0. Now think about this in terms of the mechanical system, okay, because that would be easier for you to understand. Okay, think about this in terms of the mechanical system. Okay, what was the transfer function of the mechanical system, of the mass spring damper system? Recall, the transfer function was essentially 1 divided by ms square plus bs plus k, where m was the mass of the mass block, b was the damping constant, okay, and k was the spring constant. Okay, just don't confuse damping constant with damping ratio. So what we essentially did, we divided the numerator and the denominator with 1 by m. So divide those by 1 by m. So I would have s square plus b by m s plus k. And let's tally this transfer function. So I have this transfer function, which is 1 by m divided by s square plus b by m s plus k. Let's tally this with the standard form of the second order transfer function, which was omega n square divided by s square plus 2 zeta omega n plus omega n square, right? Now of course we have chosen zeta to be equal to 0. Now in our particular scenario, zeta is equal to 0, right? Because we are looking at a particular scenario, right? Zeta is equal to 0. So we essentially don't have this term. So this is essentially 0, right? Because zeta is equal to 0. So this term has to be 0. So this b by m term has to be 0. So essentially if zeta is equal to 0, then sorry, this has to be k by m. Sorry for that. Somebody is saying what? Okay. Sorry. Really sorry. Yes. One of you have figured out the point here. So this has to be 2, right? This was supposed to be 4. Okay. Yes. Nice. All right. So this is essentially pi by 2 omega n multiplied with n. N becomes 1, 2, 3, 4, such and such. All right. Now, if zeta is equal to 0, then look at this term here. Okay. If zeta is equal to 0, then b by m has to be 0. Now, of course, m cannot be 0, because if m is 0, m cannot be infinity. If m is infinity, then we have a problem, right? We have 1 by infinity. That will be an undetermined term, right? Indeterministic term, right? If m is infinity, in that case on the numerator we have infinity, so that cannot happen. Someone is saying cosine pi by sorry, what are you saying? So yes, cosine, so for example, cosine omega n t at t equal to 4 pi by omega n, that will be equal to 1. So this is going to be 1, right? If this is going to be 1, in that case the output is going to be 0. We have 1 minus cosine omega n t, right? Okay, so that's b by m. So of course the valid condition that could happen is b equal to 0. So we don't have any damper. Now one of you asked in the last one, okay, one of you asked in the last discussion where we were discussing mechanical systems, we said, you asked that, okay, what will happen if for that particular mechanical system I do not put the damper or do not put the spring. Now here b equal to 0 essentially means that I do not have the damper. I only have the spring attached to the mass. And once again you have to recall that this was in the vertical configuration. Okay, this is not that some horizontal configuration like that. So we are essentially taking care of all the weights and acceleration due to gravity, everything, right? So this was the damping constant here. Okay, and again this was the displacement here. This was the force applied on this, and this was the instantaneous displacement. So xt, the ft was the force and xt was the instantaneous displacement, right? So essentially what it means is that if I apply a force like this, what happens? This spring pulls it in the opposite direction, but since there is nothing to damp the system, what happens? The response of the system oscillates. The response of the system becomes oscillatory, which means if I have zero friction whatsoever, right? If I have zero friction whatsoever and I have an ideal spring attached like this and we have a mass attached like this, what if I pull the mass? Okay, if I pull the mass, what will happen? The spring will pull it back. So the spring pulls it back, right? So once the spring pulls it back, it goes back to original position, right? And then again, due to that inertia, the spring once again goes back. So the spring once again goes back, right? So essentially what happens? You have an ideal spring and then you have a mass, and since there is no damping, there is no damper here, what happens is that once you pull it and release it, it keeps on oscillating forever. Okay, it's slightly more complicated than that, but you have to understand it this way, right? So the spring essentially pulls and then that force comes back. Okay, so the spring compresses and stretches indefinitely. Okay, so the spring compresses and stretches indefinitely since there is no damper to destroy the energy content in the system. So this is like an LC circuit. In an LC circuit, there will be no component that destroys energy. Essentially, a resistor would be equivalent to the damping factor here. The point being, if you have an ideal spring and you have a mass, okay, and if you pull the mass, okay, apply certain force on the mass, what will happen? Since there is no friction, it will never stop. It will keep on oscillating. Something that you probably have studied in your school level physics, right? Okay, friction is the thing that is responsible for destroying energy, for example, in rectilinear motions, right? So it's a rectilinear motion system with rectilinear motion, and here, if you don't have any friction, namely a damper was acting based on viscous friction, right? Viscous damper. So since there is no friction here, what happens? The system oscillates forever. But what is the frequency of oscillation? What is the frequency of oscillation here? For this one, the frequency of oscillation, frequency at which the response of the system oscillates, is equal to, as you can see, so what is the time period of oscillation here? What is the time period of oscillation? Of course, the time period of oscillation, if you look very carefully, the time period of oscillation is one complete oscillation here. So that is the time period, we define it with capital T. So that is going to be 4 pi by omega n, right? That's one complete oscillation, right? Or is it so? Oh, sorry. One complete oscillation is this one, right? Here starts from 0 and then goes to 2 and then comes back to 0, right? So this is one complete oscillation, right? So this is one complete oscillation. If you look at it, so that's one complete oscillation. Then this is one complete oscillation. All right. So one complete oscillation takes this much amount of time. So that takes 2 pi by omega n amount of time. Now, if I ask you, what is the frequency of oscillation? So what is the frequency of oscillation? We represent that with omega. All right. So, and omega is of course 2 pi by n, 2 pi by t. And if you do 2 pi by t, that becomes omega n. So what is omega n? So omega n is essentially the frequency of oscillation for the output when there is no damping. So I can say that when a second order system is excited with a unit step input, the output, rather the response, becomes an oscillatory signal with a frequency of omega n radian per second. Okay, second, when zeta is equal to 0. Now try to understand the mathematics behind this. Okay, when zeta is equal to 0, the response of the system never decays, right? The output of the system never decays. It stays oscillatory forever, because those damping term is responsible for spending the energy contained within the system, right? So if I have an ideal situation here, like I have a mass and a spring, there is no friction whatsoever, that energy contained in the system when I apply a certain amount of force will never be released out of the system, right? That energy will never turn into heat and get released. That is never going to happen. And since that is never going to happen, that energy will turn out as the oscillation of the system. So output of the system will never decay. It will never become 0, right? It will never become 0. And so this zeta equal to 0 is known as an undamped condition. Okay, zeta is the damping ratio, we call it damping ratio, and since zeta is equal to 0 under this condition, this is called undamped condition, right? So zeta equal to 0 essentially means undamped condition. So the condition for which we are figuring out the output is the undamped condition, right? So here the system is undamped, so there is nothing to damp it. Of course, I would suggest you go through the electrical counterpart of this, and you will see if the resistance value is 0, if R is equal to 0, in that case the same thing will happen. You will end up with something called an LC oscillator, right? So undamped, and when the system is undamped, this is the frequency at which the response oscillates. Okay, so this is the frequency at which the response oscillates. So this frequency is known as the natural frequency. And again, the term natural, I'm going to kind of vaguely tell you that since it naturally oscillates at that frequency. But what I mean by natural, yeah, that will be discussed later on, rather. Okay, but just keep in mind that kind of, in a sense, that the response of the system turns out to be oscillatory naturally, more or less naturally, right? So this frequency in particular is known as undamped natural frequency. So when there is no damping, when there is zero damping in the system, so undamped, for an undamped system, this is the undamped natural frequency. I think you now understand why we had omega n squared, just to make sure that the undamped natural frequency turns out to be omega n. Okay, so for this system, the frequency of oscillation when there is no damping would be omega n, right? Now here in this particular example, omega n would be root over, so omega n square would be k by m, so omega n would be root over k by m, right? So if we have a higher spring constant, the natural undamped natural frequency, the frequency at which the response oscillates, will be higher, so it will be a faster oscillation. And if the mass is larger, of course the spring will have a hard time to pull the mass and push it back again, right? So the frequency will be smaller, so it will oscillate but slowly. That's quite easily understandable here, right? So that's the undamped natural frequency for this particular scenario. What about the RLC series circuit? If you recall the RLC series circuit, the undamped natural frequency, the transfer function for an RLC series circuit would be 1 by LC by S square plus RC by LC. So that's R by L S plus 1 by LC, right? So that's RLC series circuit, and this is versus once again omega n square divided by S square plus 2 zeta omega n s plus 1 by LC. Just keep in mind that for the previous comparison we had a multiplying factor here, otherwise things won't work. Now the point being, here for this system, that will be omega n square. So here for this system we have a value of omega n. Omega n square is 1 by LC, so omega n is root over LC. And if you recall that this is known as the frequency of resonance, right? So this is the resonance frequency. Resonance frequency for an RLC series circuit. So what is the resonance frequency? Resonance frequency is essentially, okay, just one more thing, when zeta is equal to 0, that can be achieved by making R equal to 0, right? When zeta is equal to 0, this can be achieved by making R to be equal to 0, right? When R is equal to 0, zeta is equal to 0, right? So when there is no resistance, so essentially when I am talking about something like this, when I have a when I have an inductor and a capacitor, okay, and I excite the system like that, the input is a unit step, this is L, this is C, okay, the output is going to be oscillatory like that, okay, the output is going to be oscillatory, okay, and the frequency of oscillation would be 1 by root over LC, okay. So this frequency of oscillation is known as the resonance frequency. So for an RLC series circuit, if the resistance is 0, then the output becomes a pure oscillation, an oscillation that never decays, okay, an undecaying oscillation, for example, and the frequency of that oscillation is 1 by root over LC. This frequency is known as the undamped natural frequency, right? So you can understand what is the thing that actually damps the response. That would be the resistor for an RLC series circuit, and that would be the damper for the mechanical system, right? So a damper is responsible for spending energy, right? Spending energy. And similarly, a resistor is responsible for spending energy, right? Of course, you people know already that for an ideal capacitor can never, what should I say, spend energy in a sense, right? If you apply a sinusoid to a pure capacitor or a pure inductor, then in one cycle of the sinusoid, the capacitor or the inductor will store energy, and in the next cycle, it will release that energy back to the source, right? Then again, in the next cycle, the capacitor or the inductor stores energy and then it releases it back to the source. Like that, keeps on happening, right? So capacitors and inductors, they cannot spend energy. They can only take energy in one of the cycles and release the energy back to the source in another cycle, right? So that keeps on happening. Here in this one, so here in this one, what happens is that in one cycle, what happens, the capacitor gets stored with energy, and then on the next cycle, that energy is released and that is stored by the inductor. And on the next cycle, what happens, next part of the cycle, the inductor releases the energy, okay, and that is stored in the capacitor, and that keeps on happening. Okay, since there is no resistor here, there will be no copper loss here, so essentially there won't be any I square R loss. So, and that I square R loss would have reduced the total energy content in the system, right? But since that is not there, that energy is never spent in a sense. Now similarly, look at this one here also. Since there is no damper, the energy is never spent, right? So if I pull the mass in this direction, the spring actually stretches out. So the spring applies a force in the opposite direction. So the mass moves in the opposite direction, right? And then when it has finished moving in the opposite direction, then the spring gets compressed. Then the spring tries to expand once again. So when the spring tries to expand once again, the mass again moves in the other direction, okay? And when the mass moves in the other direction, again the spring stretches, okay? And when the spring has stretches to its final position, then it wants to go back to its original position. So it tries to go back, and then it gets compressed. And this keeps on happening forever if there is no friction. There is nothing that can spend energy in a sense, right? I think you understand my point here. That's undamped situation, and that is why omega n is known as the undamped natural frequency of oscillation. All right. So we have quite a lot to discuss. Let's jump to the next condition. So we have successfully figured out the response of the system, or rather the step response of the system, when the value of zeta is equal to 0. So the undamped situation essentially, right? So then let's look at the next condition when zeta is strictly between 1 and greater than 0. Strictly between 1 and 0. Okay, and you will see what the name of this one is later on. Okay, but for the moment, let's see what is the output. Of course, the Laplace transform of the output is once again 1 by s into omega n square by s square plus 2 zeta omega n plus omega n square. All right. So, okay, along with all these things, there is one more thing I should tell you. Is the location of the poles and zeros of this system. So if you have this configuration, this scenario, okay, what are the poles and the zeros of the system? Okay, what are the poles and the zeros of the system? If you think about it, so this is my S plane, okay, this is sigma, and this is S plane. Let me write the real part of S and the imaginary part of S, okay, and the imaginary part of S. All right, so this is 0, of course. Of course, how many poles does the system have? It has 2 poles, right? And what are the values of the poles? Of course, if I calculate this, s square plus omega n square equal to 0, if I solve this equation, I would get s equal to plus minus j omega n. Okay, so plus minus j omega n. So the values of the poles are plus j omega n and the minus j omega n. This is how we denote poles, right? So this is plus j omega n and this is minus j omega n. So these are the two poles of the system. Now omega n could be a small value, could be a large value, based on that. Could be different things. Right? So these are the poles and zeros for the transfer function gs. Right? Got it? So this was essentially your gs, right? So this is your gs. I think you understand that, right? There is nothing difficult to understand. Of course, there is no zero. There is no finite zero example, right? Okay, all right. And with that said, now consider this condition, right? Now, of course, before I can even proceed or do anything with this, let me try to figure out the partial fraction expansion here. Okay, let me try to figure out the partial fraction expansion. Again, on the denominator, let's try to at least do something with the denominator. Okay, let's try to do something with the denominator. Let's see what I can do. So I have 1 by s and then multiplied with omega n square. Now we have heavy mathematics ahead, so be sure to follow it properly. So we have 2 zeta omega n, and I did forget to write s here, zeta omega n s plus. So now let's try to write this as a complete square. So I have s square, then I have 2 zeta omega n s. So if I had zeta square omega n square, that would complete the square here, right? That would essentially make this thing s plus zeta omega n whole square, but I don't have that. Instead I have omega n square, so I would write omega n square and subtract zeta square omega n square. Got it? All right, so we have that. So essentially we have added zeta square omega n square, right? So 1 by s, and then on the numerator I have omega n square, and here this becomes s plus zeta omega n square, and then plus I have something like 1 minus, so out of these two I can factor out omega n square, so I would have 1 minus zeta square omega n square. Okay, got this? So let's simplify this slightly. So I would write 1 by s, and then this would be omega n square. This is s plus zeta omega n whole square. So let's try to write this as something square plus something square, just like the previous one. So in the previous one I had s square plus omega n square, but instead here I would have s square plus root over 1 minus zeta square omega n whole square. Okay, something like that. Okay, so we just taken a square root of the whole thing and written it as a square, right? And let me just write down something here. So 1 by s, let me just simplify this notation here. So I'm writing s plus sigma whole square plus omega d square, where I'm assuming sigma to be equal to minus zeta omega n and omega d to be equal to root over sorry, sigma is equal to zeta omega n and omega d is root over 1 minus zeta square omega n, right? So we have just written two factors here. So that's my Laplace transform of the output and Laplace transform of the step response essentially. All right. All right, so I think we are back, and this is becoming a serious headache for me. Right. I think some of you have joined back in, so let's start our discussion. I think this is working now. All right. All right. So, and this time around, this wasn't the ISP. It was the electric utility company here. They are apparently doing something. All right. So we were discussing this, right? So we have this. Of course, we have. Let me write it down. So this was S plus. So just so those of you who have forgotten what we were actually dealing with, we were trying to figure out the inverse Laplace transform of this when zeta wasn't 0, right? When zeta was between 0 and 1 strictly. So this is the output of the system, right? And rather, this is the Laplace transform of the output. Got it? Okay. So with that said, let's now again do the pole zero map here, just like this one. Let's figure those out first. Okay. So of course, this is the transfer function we have been looking for. This is the transfer function. This is your GS essentially. Okay. This is your GS essentially. That's GS. Okay. So right now, of course, this is the real part of S, and this is the imaginary part of S. All right. And if you take the denominator as polynomial, we have S plus sigma whole square plus omega d square, that's equal to 0. So if you take this, this becomes S plus sigma whole square is equal to omega d square. And if you take the square root on both sides, it becomes S plus sigma equal to plus minus j omega d, because you are taking a square root over this. So of course that becomes a plus minus j omega d. So with that said, S becomes minus sigma plus minus j omega d. And of course sigma and omega d have been defined already. Sigma has this value and omega d has this value, right? So essentially these are denoting points here. So somewhere around here, somewhere around here, and somewhere around here. Okay. So where this distance is sigma, and this height is omega d. So this is sigma plus j omega d, and this is sigma minus j omega d, right? So minus sigma, right? Minus sigma minus j omega d. So those are the locations of the poles, right? In this one, right? So now before I can proceed and do the inverse Laplace transform, let's do a partial fraction expansion. Okay, so this, let's do a partial fraction expansion. So let's consider this one to be on the left hand side, 1 by s square multiplied with omega n square divided by s plus sigma whole square plus omega d square. And on the right hand side, let's again write it as a by s plus, so this would be identical to bs plus c divided by s plus sigma whole square plus omega d square. Okay, so with that said, so again let's do that. Okay, if I check the identity on the numerator, this becomes a multiplied with s plus sigma whole square plus omega d square plus s into bs plus c, and this is equivalent to omega n square, right? So with that said, let's again simplify this even further. I mean, let's use the techniques to figure out the values for a and b and c, right? So let's put s equal to 0. That's the first thing we would do, right? Let's put s equal to 0. Again, once again, this is an identity. So if I put s equal to 0, so I can put any value of s, but the identity would still hold, right? So this is, if I put s equal to 0, then I would have a multiplied by sigma square plus omega d square, and this becomes 0, that becomes omega n square. All right, I think, did I make any mistake here? Alright, I don't think I have made any mistake. Alright, so A would be omega n square by sigma square plus omega d square. Got it? Alright, so again, before I proceed, let's simplify this. What is omega n square? That's a parameter predefined. What is sigma square? We defined sigma to be zeta omega n, so that's gonna be zeta square omega n square. And what is omega d? We defined that to be root over 1 minus zeta square omega n, so that becomes 1 minus zeta square multiplied with omega n square. So if you simplify this, this becomes omega n square divided by zeta square omega n square plus omega n square minus zeta square omega n square. So essentially I would have omega n square, which is essentially 1. So we figured out that A is just 1 after simplification, right? A is just 1. We are still yet to figure out B and C, and for those we are going to use the same technique as we did before. So let's compare the coefficient of S square. So again, if I expand this on the left hand side here, so I would have S square plus 2 sigma S, okay, plus sigma square plus omega d square. So the coefficient of S square would be A, and here if I expand this, the coefficient of S square would be B. So the total coefficient of S square on the left hand side is going to be A plus B, and on the right hand side the coefficient of S square is 0. So those are going to be identical. So A plus B is going to be 0. So with that I have B to be equal to minus A, that's minus 1, right? Alright, and similarly let's compare the coefficient of S. Okay, here what is the coefficient of S? Look very carefully. What is the coefficient of S? That's going to be 2 sigma, right, and multiplied with A. So that's going to be the coefficient of that one. So 2 sigma A, and here if I expand this, that's going to be C, right? So the total coefficient of S on the left hand side is going to be 2 sigma A plus C, and that on the right hand side is 0, of course. So I'm going to get a 0 here, and C is going to be minus 2 sigma A. And of course I already know what the value of A is, so I get C to be equal to minus 2 sigma, because A has already been proven to be 1, right? So I have 2 sigma S by A. I think I have done it correctly. All right, so as I was saying, this was the partial fraction expansion of this thing, right? So let's pull it here. So this was ys, therefore ys, which is equal to 1 by s multiplied by omega n square divided by s plus sigma whole square plus omega d square, could have been written as a by s plus bs plus c divided by s plus sigma whole square plus omega d square. Now we have figured out the values of our a, b and c. Let's put those values here. So of course a has a value of 1, b has a value of minus 1, and this is minus 2 sigma, right? So this becomes 1 by s. So I'm taking minus common out of these. Okay, so b has a value of minus 1, so that becomes a 1, and c has a value of minus 2 sigma, so that becomes plus 2 sigma, and I have divided by s plus sigma whole square plus omega d square. All right, and I'm doing a one more step here. I think this would be obvious, right? So I'm writing this numerator as s plus sigma plus sigma. Of course I can do that, right? That was s plus 2 sigma. So this becomes s plus sigma square plus omega d square, and with that said, this becomes 1 by s minus s plus sigma divided by s plus sigma square plus omega d square, and minus sigma by s plus sigma whole square plus omega d square. So that's our total partial fraction here for ys, right? That's ys. But before I jump and figure out the inverse Laplace transform here, let's look at a few things. Okay, let's look at the Laplace transform of this. Let's look at the Laplace transform of sine omega dt. What is the Laplace transform of sine omega dt? Of course with ut. sine omega dt ut. What is the Laplace transform of that? That's going to be omega d divided by ss square plus omega d square, right? All right. Now question is, what is the Laplace transform of e to the power minus sigma t sine omega dt sine omega dt ut. So we know the Laplace transform of sine omega dt ut. So we're multiplying that with e to the power minus sigma t. I want to figure out the Laplace transform of that. So we're going to apply the frequency shift theorem. Okay, and essentially this becomes s replaced by s plus sigma. So that's one of the properties of Laplace transform that we actually derived. So this is going to be s plus sigma, right? That's omega d square, and d is again in subscript. Okay, d is subscript. I think it's understandable. So this is omega. Got it? So that's what it is. So now, of course, if I multiply, okay, leave that as it is. So we figured this out at least. Let's figure out something else. Let's figure out the Laplace transform of cosine omega d t ut. Okay, and we know that to be equal to s by ss square plus omega d square, right? So what is the Laplace transform of e to the power minus sigma t cosine omega d t ut? Again, the same thing would happen. S will need to be replaced by s plus sigma. So this is going to be s plus sigma divided by s plus sigma whole square plus omega d square. Let's bring this again. Right? So we kind of know these things already, right? By virtue of attending previous classes, hopefully. So we know that, we know these things. So with that knowledge, let's simplify this. Let's write this as 1 by s minus s plus sigma divided by s plus sigma whole square plus omega d square. So that is omega d square plus, minus. We have sigma, and this sigma I am writing this as, try to understand, I'm writing this as omega d. Okay, let me show you what I mean. So I'm writing this as omega d. So in the denominator I have s plus sigma whole square plus omega d square. How long have I taken? I'm not sure. Let's see. How long is the stream going? 1 hour 15 minutes, right? Okay, so I have, if I write omega d here, I have to make sure that I do certain manipulation to make sure that's sigma, right? So I'm just multiplying with sigma by omega d, so that omega d cancels out. Okay, so we have this term. So let's bring this back here. So that's my yt, sorry, ys, that's ys. So therefore ys is equal to this. All right, so then of course if I take the inverse Laplace transform and figure out yt, so that's going to be ut. Of course, inverse Laplace transform of 1 by s is ut minus. Now what is the inverse Laplace transform of s plus sigma divided by s plus sigma whole square plus omega d square? Of course, that is e to the power minus sigma t cosine omega dt ut. We just figured this out moments ago, right? So this is going to be e to the power minus sigma t cosine omega d t ut. Again, ut is there just to ensure that the value of the output is 0 before t is equal to 0. Okay, and here I have minus sigma by omega d product. Now of course, what is the inverse Laplace transform of omega d divided by s plus sigma whole square plus omega d square? Of course, that is e to the power minus sigma t sine omega dt ut. So that's going to be e to the power minus sigma t sine omega dt ut. Let's take ut common out of everything. Okay, that would be a good job here. So I have 1 minus, and let's also take minus sign common out of this. Let's also take e to the power minus sigma t common out of this. I am then left with 1 minus e to the power sigma t, and then I would have a cosine of omega dt plus sine plus sigma by omega d sine of omega dt, and the whole thing multiplied with ut. Again, the sole purpose of ut is to make sure that the output is causal, right? because the system is causal, input is causal, the output has to be causal. So that's your output, right? So that's kind of the end of it. But we are going to bring it, we are going to actually go a bit further out of this. But as far as the output of the system is concerned, this is the output. But from this, you might not be able to figure out how that output looks like. Okay, you might not be able to figure those out. In that case, let's simplify this slightly more. Okay, let's bring this and let's copy and paste this, right? Hence, I can copy paste. So this becomes okay, let's, instead of copying and pasting, let's just write it down. So I'm taking omega d common out of these. So if I do that, let's just see what happens. So this becomes, if someone is asking any question, okay, so this becomes 1 minus I have seen some people who joins just for the attendance and then simply leaves the class, has been doing for a very long time, but I don't really care. So we have taken omega d common out of this, 1 by omega d common out of this. So I think this is kind of understandable, right? Right. Now let's do a little bit simplification here, little bit of a simplification here. Okay. So let's recall our pole zero picture here. Okay. So this is again called a pole zero map. This figure is known as a pole zero map. Let's bring this here, or rather let me draw it once more. Okay. Let me draw it once more so that this is properly understandable again. Let's see the pole zero map. Okay. Again, I'm drawing a few things, so don't worry about it much for the moment. I'm going to explain what I'm drawing and what I'm saying here. Let's look at the pole zero map. So let's look at the location of the poles that we actually told you moments ago. Right? Again, this is the real part of S, and this is the imaginary part of S. Okay. All right. So, and I said that the poles for this one would be located at these, right? Of course, if I simplify this, it's going to be minus sigma plus minus j omega d, right? So minus sigma plus minus j omega d. So now look very carefully. So this is the location of the pole. So one pole would be located here, and another pole would be located here, somewhere like that. So this is one of the poles, and this is here is another pole, right? So again, poles are denoted with cross symbols like that. Okay, is it visible? I don't think so. Okay, so one is here and one is here. What is this circle? I'm going to explain that. Okay, just keep in mind that this is a pole which is at minus sigma plus j omega, and this is another pole which is at minus sigma minus j omega, because we solved the denominator's polynomial and figured out that these were the pole locations, right? So now if I just draw it a bit, you will see that, of course, if I draw a vertical line joining these two poles, then this length is sigma, right? This length is sigma, this length is sigma, from this point to this point from the origin, this length is sigma, right? Okay, and what about the height here? What about the height here? The height here is omega d, because that's j omega d, right? So this is omega d, so this height here is omega d, right? This is omega d, this height here, this is omega d, and this length is sigma. Of course, it's on the other direction, so it has a negative value. So that's your sigma, right? All right, so that's fine and all. But what if, okay, let me just make this figure slightly bigger. Good. All right, so let's do certain simplification. Let's figure out the distance of the poles from the origin. Okay, let's figure out the distance of the poles from the origin. Let's use another ink. So let's draw a line joining the origin and the poles. Okay, and let's consider this angle to be beta. Let's just say we are just assuming things arbitrarily right now. You could call this theta, whatever you could call this. Okay? It won't matter. Okay, fine. We are just trying to figure out the length here. We are trying to figure out this orange length here. Okay. Okay. So what is the distance of the poles from the origin? Okay, direct distance here. So of course the vertical distance is omega d. What is the horizontal distance? That's your sigma. Of course the distance, essentially the poles are at s equal to minus sigma plus minus j omega d. So what is the modulus? That's the distance, right? So this is the distance of the pole. That's mod s, right? So what is mod s? That's going to be minus sigma whole square plus minus j plus minus omega d whole square. Of course that's the modulus, right? So and that becomes sigma square plus omega d square and then a square root. But we people already know sigma square plus omega d square, that's just omega n, right? Because you can write it down, right? We did it few moments ago, right? I think we wrote that, right? Yeah, sigma square plus omega d square turned out to be omega n square if you look at this one. So that's omega n square and the square root. So that's just omega n because omega n is positive, right? That's omega n. So the length here is omega n. Now look very carefully. The length with which how far away the poles are, it's omega n. Now look at the undamped situation. Look at the undamped situation. For the undamped situation, if I ask you, where is it? Yeah, for the undamped situation, if I ask you the same question, where are the poles? How far away the poles are from the origin? The answer would be same, omega n, right? The distance of any of the poles from the origin is omega n, right? Distance of any of the poles from the origin is omega n once again. Okay, just keep that in mind for a moment, right? So distance is omega n, so we have proven that. All right, so with that said, what is if I write cosine beta? Let's write sine beta. What is sine beta? Sine beta will be perpendicular by base, perpendicular by hypotenuse. So what is the perpendicular? That's omega d. And what is the hypotenuse? That's omega n, right? So we are considering this right angle triangle. So where beta is this angle and the right angle appears here, right? And perpendicular is omega n. Sorry, perpendicular is omega d and the hypotenuse is omega n, right? So omega d by omega n. Got it? Fine. Let's leave it like that. And what is cosine beta? Cosine beta would be base by hypotenuse. So what is the base? That's sigma. The length of the base is sigma. By hypotenuse is omega n. That's fine. And just so that the discussion is clear, what is tan beta? Tan beta is essentially sine beta by cos beta. So sine beta by cos beta, if I do that, this becomes omega d by sigma, because omega n will cancel out in this one. Okay, again, if you have any query, just make sure that you follow. Again, I already told you that this is going to be heavy mathematics, at least for the moment, right? Now with that said, I can write from this, I can write omega d to be equal to omega n sine beta, and from this I can write sigma to be omega n cosine beta. Omega d is omega n sine beta, sigma is omega n cosine beta. And let's pull this back here. Let me just copy and paste. That was the output of the system, or rather the step response of the system. Output of the system when the input is step. Now look at this, omega d. Now instead of omega d, I'm gonna write omega n sine beta, and instead of sigma, I'm going to write omega n cosine beta, right? So let's write those. I have 1 minus e to the power minus sigma t divided by omega d, and here for omega d, instead of omega d, I'm gonna write omega n sine beta, right? So this is going to be cosine omega dt multiplied with omega n sine beta plus, and this is going to be sine omega dt multiplied with and in place of sigma I'm going to write omega n cosine beta. Okay, I think I'm running out of space. Good thing that I can shift things around here. Okay, so I have ut multiplied there. All right, so I have 1 minus, again if you have any query just feel free to ask, e to the power minus sigma t, and just follow along the mathematics we are deriving here. Okay, so this is going to be, look at this one, this is sine a. So okay, just one more thing, let's take omega n common out of this. So omega n factors out, so I have sine omega dt cosine beta plus cosine omega dt sine beta, right? And this is like sine a cos b plus cos a sine b, right? This is just sine a cos b plus cos a sine b, so which essentially is sine a plus b, and a is this one, b is this one, right? Someone is saying, why am I not putting the value of omega d? Yes, I'm going to put the value of omega d later on. I'm just leaving it as it is because I already know the value of omega d, right? That's root over 1 minus zeta square omega n. I can put it anytime I want, right? All right, so now instead of this I'm writing, so again, so this is 1 minus, so I have omega n by omega d, so omega n by omega d. I have a decaying factor e to the power minus sigma t, and then we have sine, so it's a sine a plus b, right? Sine omega d t plus beta. Okay, so look at this response, just like the previous one, this is again a sinusoid, right? Okay, if you recall the previous response, this was just a cosine, and that's the same thing as a sinusoid, right? Not much different from this, right? Only thing is that we have a multiplication factor here, and then we have an exponentially decaying factor multiplied with it, which means that the response will no longer be purely oscillatory sinusoid, but instead, as time goes on, this factor will decay, right? As for example, when t is equal to 0, this factor is 1, but when t becomes larger and larger, this factor becomes smaller and smaller, so the oscillatory component of the response becomes smaller and smaller. Now if I ask you what is the final value of the response for this system, right? I'm asking for this. What is y infinity? Of course, y infinity can be simply calculated since we already have done the inverse Laplace transform. That's t tending to infinity on yt. Now if I put the value t tending to infinity, so this becomes a very small quantity, and this only oscillates between 0 and 1. So with that said, this is going to be between 0 and 1, but this is going to be 0, because that's e to the power negative infinity, because sigma is positive. So this entire term becomes 0, and of course ut is 1, so the output is 1. So when enough time has elapsed, the output reaches a fixed value. This is known as a steady state. If you recall, this is known as a steady state. Of course, the first steady state would be when the system is off, when there is no input, and the final steady state would be when the input has been there for a very long time, so that the output has reached a finite value, a fixed value. So this is known as a steady state. So this is a steady state, right? So when enough time has elapsed, that's the steady state. So if that is the steady state, then out of this response, again, let me just write it down. Okay, let me just write it down. Again, I'm getting rid of ut, and I'm gonna write t to be greater than equal to 0. So we have taken care of ut by writing this. So that's your output. But look very carefully. In the output, this is the steady state value. So when enough time has elapsed, this is the output of the system. So this is the steady state response. Okay. So when the system was off, the output was 0. And when the system has been on for a very long time, the output has reached a value of 1. But between that, okay, between these two steady states, between the event when the system was off and just turned on, and then before enough time had elapsed, this was the response of the system. This is the response of the system. This is the part of the response of the system that changes over time, right? Okay, when the system's response output of the system, when the system was started at t equal to 0, the output was 0. Okay, and this is the factor that determined how the sinusoid will change, how the sinusoid will decay, and eventually after enough time has elapsed, how the response will become 0. So this is what the transition looks like. So one steady state when the output is 0, one steady state when the output is equal to 1. And between those two steady states, the transition is known as the transient. And the transition, whatever behavior of the system we see during that transition, is known as the transient response. So this part of the response is known as the transient response. So this is the transition between 0 output and 1 output, right? So if I draw it, again I'm going to make a crude drawing because I did develop a nice Python animation for you. Okay, so of course the output is 0. The output is 0 before time t is equal to 0, so just like that. Okay, and after time becomes t equal to 0, the output is supposed to become a sinusoid, but unfortunately we have a, or rather fortunately for us, we have a decaying factor multiplied with it. Okay, so the output is kind of gonna look like bad drawing. So essentially, how do we draw these kind of things? We use these terms as something called the envelopes, right? And we essentially draw it like this. So the output can never reach beyond 1 and plus minus this value, right? The output can never reach beyond 1 and plus minus this. Okay, because of that, right? 1 is there and plus minus this. Okay, at any given point, the value of this factor, the transient response, is omega n divided by omega d into e to the power minus sigma t, right? So if we take that, let me just take that. Okay, so let's say so that's one of the factors, and this is one of the factors. The value can never go beyond those two values. The output can never go beyond those two values, right? Because we have 1 minus those, right? So output can never go beyond these two values. So what happens is, again, this is the final output. Okay. Now this is the final output of the system, which is of course 1, which is again the steady state response, if you understand that already. Okay. Then of course the response will never go beyond these values. No. Try to understand. This factor is always less than 0. Sorry, less than 1. This factor is never going to be greater than 1. Okay. So I have a minus sign, but this factor is never going to be greater than 1, right? Right? And you will see why, right? So the maximum value of this transient factor is 1, and the minimum value of this transient factor is 0. So this part never becomes greater than 1. So the output is never going to be negative, right? So between these two values, the output will lie between these two values, and the output will be a sinusoid, but albeit a decaying sinusoid. So the response of the system would decay over time, okay? And it will never yeah. So someone is asking something. I don't understand your question. Someone is asking, but that is not greater than 1, so the ultimate result will be greater than 0. No. Yeah. So try to understand, this factor is between 0 and 1. So this is going to be between 0 and 1. Okay, this is going to be between 0 and 1. this part is never going to be larger than 1, right? For this case at least. Okay, right? So this is the output of the system, right? So as you can see, it's a sinusoid, but there is a decaying factor simply because the system has a resistor, right? System has a factor which actually dampens the output. Okay, that is the purpose of the damper here. So that is the purpose of the damper here. So I am saying this is time. Okay, just a moment. I'm saying this is time, and this is the output of the system, but this is the damped sinusoidal response, right? Now as we increase the damping factor, of course something will happen. This decay will happen faster. So as we will see what I mean. Okay, as we increase these factors, so if this factor becomes larger faster, rather if this factor becomes smaller large faster, then the decay would happen faster, right? And if this decay happens slower, in that case the system responds differently slightly. Okay, so we are going to see that. Okay, with a suitable Python example, right? So let me, okay, just one more thing. Let's take this equation and simplify this a bit. Let's write down the more complicated version of this. Okay, so we chose omega d, we chose sigma by ourselves, right? Let's just write down. So greater than 0. So we chose sigma, we chose omega t, and let's put the values here, right? So this is 1 minus omega n divided by root over 1 minus zeta square omega n, that's your omega d, e to the power minus sigma is zeta omega n, so e to the power minus zeta omega n t, then sine omega d is root over 1 minus zeta omega n t, and plus, of course, I have to bring this here, and plus, and in place of beta I'm going to go back, and in place of beta I'm going to write beta to be equal to tan inverse omega d by sigma. All right, so so that's going to be tan inverse omega d by sigma. Okay, and what is tan inverse omega d by sigma? What is tan inverse omega d by sigma? So if you recall, omega d is root over 1 minus zeta square omega n, and sigma is zeta omega n. So this is just tan inverse root over 1 minus zeta square divided by zeta, right? So this is just like that. So this is root over 1 minus zeta square by zeta. Okay, so that's the response of the system. Now this looks pretty bad, but we are going to take care of this pretty shortly, right? Got it? Nice. Fine, that was the response, and this is something you saw in yesterday's class when we were actually doing inverse Laplace transform, right? We were actually seeing something like this. So now we have kind of calculated the inverse Laplace transform when zeta is equal to 0. That was an easy case. And when zeta is between 0 and 1. So the damping ratio is between 0 and 1. Now let's see this in action. So look very carefully. The output, what are the parameters on which the output depends? Okay, the parameters here are omega n and zeta, right? So these are the parameters on which the nature of the output depends, right? So omega n and zeta are the only parameters, right, for the system here, right? So let's look at one animation that I spent 6 hours making yesterday. So right, so now let's see an example, right? Now don't worry about these terms right now, but I shall explain everything, right? But look at the response here. Look at the response properly. All right, start. So we have chosen a situation. So this is the output of the system, right? As you can see, this is the output of the system. Now I'm saying, okay, well, there are quite a few things here. I'm going to explain those terms to you. Okay, so now look at the value of zeta. What is the value of zeta? I have chosen this to be 0.3. What is the value of omega n? I have chosen this to be 1, right? And this is the response of the system. The thick black curve here, that one is the response of the system, right? Okay, so now look at this line here. Look at this line that passes through the y equal to 1. So this is step response. Look at this line. Okay, so that's the steady state response. This line is denoting the steady state response, right? I think that's clear, right? This line is giving you the steady state response, right? Just to show you, for example, if I increase zeta, what will happen? The decay will become faster. Okay, if I increase zeta, the decay will become faster. Let me just go to this one. Okay, let's look at this one. So if I increase zeta, of course the value, if I increase zeta, the decay will happen faster because I would have a larger negative factor on top of exponential there, right? So with that said, if I increase zeta, let's increase zeta a bit. Okay, when zeta is increasing, what is happening? Forget about all these lines and everything. Okay, look at the black curve here. Okay, someone is saying it has crossed this envelope here. Yeah, this is because the way I have drawn it. Okay, this is because the way I have drawn it. Yeah, this is the heavy computation, right? At every instance, it is calculating everything and plotting everything, right? This is not a very easy calculation for the computer, at least, right? But look at the black one here. Look at the black curve here. Okay, the response here. When the damping ratio is low, what happens is that the system takes longer to decay, right? The response takes longer to decay, right? And of course, there will be a drop in performance in OBS because this is taking a lot of CPU power. As I increase zeta, what is happening? As I increase zeta, the response becomes the transient decays faster, right? So before t equal to 0, the output was 0, and after a long time has elapsed, the output has become 1, right? Look very carefully. The output has become 1 after a long time has elapsed, right? And between those two, whatever changes I see, all these nature of the output, right? So the output changes between those two values. That's the transient, okay? And if the damping ratio is faster, then what is happening? What? Hold on. I think this is fine, right? All right. So when damping ratio increases, what happens? The transient decays faster, right? Let me make the damping ratio even larger. So the transient decays even faster, right? The sinusoidal nature is hardly visible now, right? The sinusoidal nature of the response is hardly visible. Let's make this even larger. Let's make this. I think I need to get rid of the envelopes. The envelopes are kind of distracting here. Hold on for a second. I need to get rid of the envelopes. Nice. Gotten rid of the envelopes. Okay. Make this a very large value. Right? So that peaky nature is gone, right? Kind of. And don't worry, this is advanced Python programming, right? Of course. Right. So of course, now here in this example, zeta is 0.88 and omega n is equal to 1, right? All right. So let's go back with smaller values. Now we have made zeta to be equal to 0.3. And don't worry, OBS is going to lag, because this computation is taking a lot of, right? All right. So this is again the response that I tried to draw, at least, right? With pen and paper, right? Sort of, right? So now, so if I ask you, how would you describe this transient response? How do you describe this transient response? Now, if I ask you, how do you describe this steady state response? Of course, you can describe the steady state response pretty easily. How do you describe the steady state response? By just saying, okay, before t was equal to 0, it was in one of the steady states, so the output was 0. And after enough time has elapsed, okay, the output has reached 1, right? So that's one steady state. This red line is denoting a steady state, right? But if I ask you, how do you denote the response of the, how do you kind of characterize the response of the system? Recall, for first order systems, we did characterize the response of the system by just knowing the time constant of the response, right? But now here, I cannot just be happy with the time constant, because there is no time constant, right? There is no question of time constant for a second order system, right? Because there is no time constant for the previous one, right? Like the previous one. For a first order system, the entire behavior of the response is determined by the time constant. But here, for the second order system, it is determined by two factors, zeta and omega n. And they would determine how peaky the response would be, okay? How quickly the transient would decay, okay? How fast or how slow the response will become. And there is one more thing, I haven't shown you what happens when I increase omega n. Of course, let's increase that. If I have increased value of omega n, so this is what happens. I'm going to explain what I mean here. So again, undamped natural frequency, omega n is undamped natural frequency. So that frequency is increasing here. So of course the oscillation will happen faster. Okay, the rate of oscillation will be faster, right? The frequency, underlying frequency of the oscillation will be faster. Okay, but the nature won't change. Look at the peak here, look at these. The nature won't change, but only there will be an expansion or a contraction along the time axis. Something that you have seen previously. All right. So now let's discuss these factors here. Okay. So in order to describe this response, we need four parameters to talk about, right? So we need these parameters. See, if I tell you about these four parameters, you would see that the understanding would be pretty complete. Okay. I would say I have a second order system, and in the response of which the system reaches this value. Okay, so see, try to understand. The output rises gradually, and when it reaches a certain amount of time, then for the first time the output reaches its supposed final value. What is the final value of the response? That's 1. After a certain amount of time has elapsed, the output reaches the supposed final value for the first time. This time is known as the rise time. This time is known as the rise time. So this is the amount of time the system takes to rise up, in a sense. Okay, this time is known as the rise time. So let me just do one thing. Hold on. Okay. All right. So this time is called the rise time, right? So I think you understand the time it takes to rise up to the final value of the response for the first time is known as the. Someone is saying when zeta and omega n are both high, right? yeah, when omega n is very high, it goes up faster, and so ultimately the response become something like this. I shall talk about that. Yeah, I'm going to talk about that. So TR here, this factor. So the time it takes to reach the final value for the first time is known as the rise time. So this is the rise time. So the time it takes to reach the final value for the first time. So let me just write it down. So TR is known as the rise time. So which is defined as the time it takes to reach the final value for the first time. All right. Then it again rises up beyond that. Okay, it goes up beyond that and it reaches a peak. Okay, this is a peak. So basically what happens, this one is the final value of the output, right? And before it can reach the final value of the output, it can peak up. It will automatically overshoot the output. So the output is overshooting the final value of the response. Then the output is undershooting the final value of the response. Then again overshooting, undershooting. So oscillation, but oscillation will automatically die down, right? Right? So this is the rise time. Now here, this is called the peak time. The time it takes to reach the peak value of the response, right? So this is defined as TP and it's called the peak time. And of course it is the time taken to reach the maximum value of the output. Okay, so time taken to reach the maximum value of the output, right? So this is called the peak time. That's right. I think this is understandable. And okay, and when it reaches the peak, try to see how much did it go beyond the final value, right? How much was the overshoot? So this much was the overshoot. If you look very carefully, this much was the overshoot, right? This much was the overshoot, because this red line is denoting the final value of the response, and this much is the overshoot, right? So this is denoted by MP, or sometimes known as peak overshoot. Peak overshoot. Right? Again, I wrote the program to calculate everything while I go. So for here, for example, peak overshoot is 37%. So it goes beyond 37% higher than the goes 37% higher than the final value of the response. So this is going to be like 1.37, something like that. Okay. So this length is known as the peak overshoot. Okay. And then the time it takes to settle down. Let me just write down the definition of MP. MP is the peak overshoot. Amount by which the peak response. Yeah, we shall calculate everything in the next class. I was going to do it today, but unfortunately I don't have time left for today's class. Unfortunately, we are going to do that, derive those in the next one. Okay, amount by which the peak response exceeds the final value. Okay, right. And then the time it takes to settle down. And now if you say, okay, the time it takes to settle down is infinite. Now if I ask you this, okay, how much time does it take to reach the steady state? If you say infinity, that's the correct answer. But unfortunately, as engineers, we cannot deal with infinity, right? What is infinity, right? Infinity is a very long time, but how long is very long? Question is how long is very long? Okay, because big, small, large, these terms are relative, right? Pretty relative. So how long is very long for the system? So to define that, we defined the steady state in a slightly different way. We said that, okay, if I am waiting for the response to reach a value of 1 and get fixed at a value of 1, I shall have to wait for infinite amount of time, which I cannot do. But instead I would say, I have reasonably reached the final value when I am about 5% of the final value. So this line here is denoting the 1.05, and this line here is denoting 0.95. The red one is denoting the final steady state, which is a value of 1. So this is 5% above, 5% below. So when the response reaches that value, 5% above and 5% below the final value, okay, and there is also a criteria called 2% criteria, where we take the band to be plus minus 2%. Okay, but let's take the 5% criteria here. In the 5% criteria, we are saying that when the response reaches plus minus 5% of the final value and stays there for the rest of the time, we say that the system has reached steady state, or rather the system has settled down. The transient has died down significantly. So this time that the system takes to reach, or rather to settle down, is known as the settling time, of course. So this time is the settling time. So time it takes to settle down. Okay. Again, we could not wait for infinite time for the system to settle down, right? For the response to settle down. That cannot happen. So instead we said when I'm about plus minus 5% about the, when the response is plus minus 5% about the final value, and it does not go beyond that after a certain amount of time, then I'm considering that amount of time to be my settling time. So for this particular example, we have calculated everything, okay, and we shall see how we actually can manually calculate everything, okay, later on in the next class, and we're going to do that, right? So just keep that in mind, these in mind. Again, I shall give you the animation that I made so that you can play with it, right? Because unfortunately, if I am going to teach you this programming, I won't be able to, because this is kind of advanced Python territory here. Actually, this had quite a bit of code, but again, we shall see how we can actually figure out the characteristics. So just to go back to our discussion here, okay, for this is again just TS, the settling time. Let me write it down. TS settling time, time required for the response to settle within a plus minus 5% or a plus minus 2% band around the final value, around the steady state. So these are the 4 characteristics that we talk about when we talk about the response of second order systems, right? These are the 4 characteristics, and these are determined entirely by, so all of these characteristics are determined entirely by zeta and omega n, right? Because of course zeta and omega n are responsible for all of these things, because the response has zeta and omega n as parameters, right? Nothing else. So we are kind of going to end our discussion abruptly at this point, sort of, right? Because I was supposed to discuss quite a few things here, but just keep in mind that there is a damping for this system, but the damping is kind of designed in a way that the response still oscillates. So the response is damped, so the sinusoidal part of the response, so this sinusoidal part of the response decays, but decays in a way that the sinusoidal part is still visible, right? So that oscillatory nature is still visible, but the oscillatory nature decays. This kind of response is known as an underdamped response, and the system in this case is known as an underdamped system, right? So this scenario is an underdamped scenario. Okay, why did I write it? Okay, so this is underdamped. So the system is underdamped in this scenario when this has a damping ratio between zeta between 0 and 1 strictly. And again, I am going to be talking about electrical circuits, mechanical systems in terms of the things we develop out of these, okay, later on in the next few classes. So I think this is understandable. Right. So there are two parameters, zeta and omega n, but there are four characteristic features of the response. How long it takes for the response to rise up to the final value for the first time, then how long it takes to reach the first peak or the maximum peak, biggest peak, how big is the peak, and how long it takes for the response to settle down. So these are the four characteristics that we have for second order system. Okay, so again we are going to continue this discussion on the next one. So thank you very much for patiently waiting here, and if you have any query, just ask. Otherwise we are going to end our discussion at this point, and I will see you on the next one. And just one more thing, I shall give you the animation, but it can be only run if you have a local Python installation, like if you have Anaconda distribution installed in your computer. This doesn't work on Google Colab. All right, so thank you very much, and I shall see you next week.